So now we get to move into different types of models that we can use for time series forecasting. We're going to start with the most basic, simplest one there is. So this is if we plot the data to look at it, visualize it, and we see a horizontal pattern. So nothing that looks like there's a trend, upward or downward, linear or exponential, that kind of stuff. And there does not appear to be seasonality. That's the repeated patterns of up and down, the peaks and troughs. So if we think that we have a stationary pattern, then that's the easiest thing we can do. There's a bunch of different models that we can look at that can do that. So we're going to look at a few of those. They're much easier to forecast because they are flat or stationary. There's just stability or constant to it. All right, so let's look at a couple of different models. So mathematically, it's represented as y sub t is equal to beta sub 0 plus epsilon sub t. Y sub t is the value of the time series at time period t. Beta sub 0 is the unchanging mean value of the series. That's the thing that's telling us what the horizontal pattern looks like. And epsilon sub t is that random error term around the pattern, that flat pattern. So yes, it will not be a straight horizontal line. There will be, when you do a line plot, there'll be some ups and downs, but we think that's just random error terms, random noise. So what we're trying to do for a stationary time series is come up with a good prediction for the beta sub 0, the thing that we're going to call the signal. That's the mean value that we think is unchanging. And the noise is simply the epsilon sub t at each time period that's around that signal. So to use these models, we often assume that the epsilon sub t are independently, normally distributed random variables with a mean of 0 and a constant variance. So what does independence mean? Well, it means that each epsilon sub t, so e sub 1 and e sub 2, are independent of one another. They do not influence each other. There are many cases in time series where this is not true, so we would have to do some kind of transformations and some other stuff to take care of that, some differencing things like that. We will not get into that. We're going to assume that for our purposes, most of the times the errors are independent of one another. Normally distributed with a mean of 0 means that the center point is 0 and all of the error terms fall into that nice bell shape around 0. So we'll have some positive errors, some negative errors. Most of the errors, right, plus or minus 2 standard deviations, will fall, or 95% of where the errors fall. And then the constant variance means that the variance between time periods for the errors does not change. And we saw some patterns back in one of the previous videos that showed us when the variance might change and what that looks like. It was that shotgun spray pattern. So one of the things we can do to see if the time series is stationary is first plot it, do a line plot, and then if it looks like it's relatively flat, or if we think there looks to be a linear trend, then we can actually statistically test whether or not there's a linear trend. We do that by running a simple linear regression. The y sub t is equal to beta sub 0 plus beta sub 1 times t, the time period index, plus the epsilon sub t. So if beta sub 1 is equal to 0, then no trend exists. Why is that? Well, if beta sub 0 is 0, then that middle term, beta sub 1 times t, drops out. And so the increase or decrease, depending on the sign of beta sub 1, no longer exist. So it drops out and we're back down to our original model for stationary, beta sub 0 plus epsilon sub t. So we conduct the following hypothesis test, just like we did in the last unit. H sub 0 is equal to beta 1 equals 0. The alternative, beta sub 1 is not equal to 0. So suppose we did this hypothesis test, which we could do either by running a simple linear regression and looking at the p-values on the coefficient for that variable, and received a p-value of 0.03. What does this mean? So the small p-value means that we do not believe the null hypothesis. So we would reject the null hypothesis, especially if our alpha value, our significance level, was 0.05. So we would reject the null hypothesis and tend to believe that beta sub 1 is not equal to 0, the alternative. So if it's not equal to 0, then we would have a linear trend. Then we could not use stationary models, the ones that we're going to look at. All right. So if it's a larger p-value, say 0.29, then that gives us more belief about the null hypothesis, meaning that it is 0, meaning that there's no linear trend, meaning that we might have a stationary process, and we should go forth by looking at stationary models. So for this, when we're looking at stationary models, we should do a simple linear regression, make sure there's no trend, large p-value on the beta sub 1 for the variable for time period index, and then go forth with stationary models. So if we have a stationary model, the simplest way to do it is to use the naive approach. And what it is it's very naive. It assumes that the demand in the next period will be the same as the most recent period. So if January sales were 68 units, then we forecast that February sales will be 68 units. Also called the last period technique. Mathematically expressed, not too interesting. We're predicting the next time period, t plus 1, that's the y hat, is equal to the most recent time period, y sub t. This is a good baseline to actually to test other models against. So it's not something that is not useful. It is actually useful as a baseline. All right, so we can baseline it against more complex models. Another method that we can use for stationary models is moving average. So this takes a series of arithmetic means and it smooths things out. So what you have to choose is the window, which is the size of the number of periods to average. So if I pick the window size of 4, then the moving average would be the most recent plus the second most recent plus the third most recent plus the fourth most recent divided by 4. Right? That's a trailing moving average, which is used for forecasting. We can also do a weighted moving average, where older data is usually less important, or people think it is. And the weights are often based on experience and intuition, where we give each of the periods in the window a possibly different weight. They could be the same. And many times we define the weight so that the weight for the most recent is at least as big as the weight for the second, all the way down to the weights for the entire window. So we could do, 25, 15. I don't know. So we could do it. The other thing we often do is add the weights up to 1. So they'd be like a point, a 0.4, a 0.2, a 0.15, and then a 0.15. Does that get me up to 1? I don't know. I didn't think about that before I started talking. So one of the reasons we do that is that when the weights are added up to 1, we can think of them as percentages. So we put, let's just do a 3 period instead of a 4 period like I have here. So if we have a 3 period, we say 60%, 30%, 10%. That's 100%, right? So we do 0.6, 0.3, 0.1. And they all add up to 1 for a 3 period moving average, weighted moving average. And what that would mean is that we think the most recent is twice as important as the second most recent. 60% is twice as much as 30%. And that one, the middle one, 30%, is 3 times as important as the one before that. 30% is 3 times 10%. So, but a lot of times those are based on experience and intuition, and they can drastically change what happens. All right, the more weight you put towards the most recent, the faster it reacts to whatever happened in the recent past. And then we also have exponential smoothing. There are lots and lots of different flavors of this. There's simple exponential smoothing, where there's no trend and no seasonality at all. So for stationary process. There is Holt-Winter's additive and multiplicative methods, which are very robust. And then many times the exponential smoothing methods are very widely used in practice because of their versatility, their robustness, their different options. They're also easy to automate. They also don't need a whole lot of data to do things, right? And so we'll look at a couple of different types of exponential smoothing the next time.